anyway, so when I calculate the exterior derivative of a 1 form, I get a 2 form, and you can kind of look at it in terms of its matrix, which is a 5 by 5 matrix. You've got all these things. So the time-space things I would identify as being an electric field. The rest of it is what you might identify as being a magnetic field. So a magnetic field, quote unquote, well, a string theorist probably wouldn't call it a magnetic field. They would call it a magnetic flux, because it really is described by a 2 form, honestly. And that 2 form has how many independent components? 1, 2, 3, 4, 5, 6. So this is really quite different than your way of thinking in 3 dimensions, right? In 3 dimensions, electric field, a vector field, 3 things. Magnetic field, it's a vector field. It's got 3 things. But when you go to higher dimensions, this duality between electric and magnetic fields, of them having being the same kind of object, it goes away. And your magnetic flux and your electric don't have to be the same kind of thing. But anyway, here, I'm interested in just the electric piece, so I'm going to assume that the magnetic piece is 0. And then we'll use these are Maxwell's equations in differential form. There it is. That's the Maxwell's equation differential form I want to write down. It's the exterior derivative of the Hodge dual of that Faraday tensor is mu naught times the Hodge dual of the current density. So this J, that J thing, it has both the charge density and also the current density. It has the rho and the J that I've talked about this semester. Charge per unit volume and also current per unit area time. Both of those things are in that script J. And when you take the exterior derivative of the Faraday tensor, you get both the equations for E and for B as they relate to the current density J. Anyway, assuming that there's no what's the word, time dependence, I think. I'm assuming that the Jm is 0, so I've just got the rho piece. Then the equation just simplifies to this. This is the analog of Gauss's equation in differential form. And then what I'll do is I'll just integrate over a 4 sphere. So basically, I look at the integral of let's see here, what is this? E wedge dt is a 2 form. I'm integrating it over a hypersphere, which is a surface here, I think. Oh, I'm sorry, I can't count. We're in where? We're in 5-dimensional space. The Hodge dual of a 2 form is a what? 3 form. So this M is a volume. I'm integrating it over the surface volume of a 4-dimensional sphere. And so that actually is this by basically Gauss's equation. This gives us the charge enclosed in this 4 volume. And on the other hand, by the generalized Stokes theorem, I can trade this exterior derivative over the bulk for a derivative of the form over the boundary. And that gives you the flux of the electric field through this 3 volume. But you guys have calculated, actually, in one of your homeworks that well, wait a minute, did you calculate? Maybe you didn't calculate that. I think you've calculated the volume of a 4-dimensional, like you calculated the volume of a sphere in 4 dimensions, right? If you take that formula and you differentiate it with respect to the radius, that gives you the surface volume. So you calculated like the 4-dimensional volume, the hypervolume of S3. If you want to find the surface volume of that, you just differentiate with respect to R. Just like if we have a circle of area pi r squared, how you find the circumference, you just, if you want to, you can differentiate with respect to R, you get 2 pi r. Right? If you take the volume of a 2 sphere, the 4/3 pi r cubed, right? Differentiate with respect to R, you get what? 4 pi r squared, which is the surface area of a sphere. This pattern continues. And so if you take your homework answer and differentiate with respect to R, you'll get 2 pi squared r cubed E, and there you go. This is Gauss's law if there were 4 spatial dimensions. It would be Q over 2 pi squared epsilon naught r cubed. We get r squared because the flux just spreads out in 3 dimensions, not 4. And so we get dropping like, we get that the magnitude depends on the reciprocal of r squared as opposed to r cubed. R cubed happens here because it's got more dimensions to spread out in, basically, is the idea. Now, obviously, I'm not going to test you on this. I just thought it might be fun for you guys to see just a little bit of a window into how this way of thinking allows you to go, and you can calculate a lot of things. If you're interested in theoretical physics, you need to learn more about differential forms, is all I'm trying to tell you. And I think it's an exciting new area of math. And even people like, it's not just, fantastic higher dimensional theoretical physics stuff, which, who knows, may or may not be physics, right? I'm not saying I actually believe that there's 5 dimensions, by the way, right? This is just a toy model. But people who study fluid physics, for example, people who really get into any kind of partial differential equations, if you get into it long enough, you'll find out that differential forms are sometimes a useful tool to studying partial differential equations. The partial differential equations are basic to all fundamental applied sciences that are worth studying. Okay, that may have been too far. But certainly like fluid physics, for example, my advisor had a son-in-law or something who was working, and he's like, I can't understand these equations. And my advisor is like looking at it, and finally he realized, oh, these are differential form equations. They're just written in engineering language, right? And so engineering has this habit of lagging about 50 years in terms of math. So if you learn cutting-edge mathematics and you combine it with the engineering that you're learning, that equals research papers. I'm not really joking. Anyway. So, anyway, I hope you enjoyed. If you didn't, I'm sorry. And tomorrow, we will spend the whole day talking about your homework. All right? So, see you guys later. Thursday. I pushed the homework back to Thursday since I'm going to spend tomorrow talking about it. I mean, why not? Since Larry talked me into pushing the math battles back. It made sense.